Hello and welcome to Engineering Simple. So last video I left off at where I calculated the zero sequence current through the low voltage winding. So now I'm going to calculate the current through the tertiary. So again, from the previous videos, basically here's the equation that I derived, which I recommend watching if you want to know how I came up with these equations. The system A plus zero sequence of the y times I0x, which I calculated here. So now it's just a matter of plugging the numbers. So 0.0096 plus 0.003 divided by the sum. And the zero sequence of the y is 0.185. And I calculated I0x to be 13.25. So if you carry out the calculation, I0y is 0.8449 per unit. So now I'm going to calculate the positive sequence current through the high voltage winding. So again, it's the same as the positive sequence current through the low voltage winding. Again, if you go to the diagrams that I drew, it will be obvious. So I'll write out the equations that I derived. Divided by positive sequence current of system B plus the positive sequence current of system A. So notice I don't write system, so it's just sys, S-Y-S, system means system B, system A, plus the positive sequence of the transformer. So the entire thing times I1. And I1 is the same as I0, which I already calculated. So now I will just plug the numbers basically. 0.065, 0.0065 plus 0.0032 plus 0.031 times 43.0045. So the positive sequence current through the high voltage is equal to the positive sequence current through the low voltage in per unit, which is 6.87 per unit. So that's the positive sequence current. So now the negative sequence, basically the negative sequence current through the high voltage and low voltage will be the same as the positive sequence through the high voltage and low voltage. But if you go through the derivation, you will get the same result. So the negative sequence current through, this negative sequence impedance of system A plus the negative sequence of the transformer. So you can see these quantities of the negative sequence current is the same as that of the positive sequence. Obviously, you can plug in the numbers and you will get 6.87 per unit, which is the same as the positive sequence. Now, the zero sequence through the high voltage winding is not the same as the negative sequence through the low voltage winding, and I already calculated the zero sequence through the low voltage winding. So the only thing that's missing is the zero sequence through the high voltage winding. So I'm gonna write the equation that I derived previously. So this is system A plus zero sequence through H times I0 X, which I already calculated. So if you just plug the numbers, 0.185 divided by 0.185 plus 0.0096 plus 0.003, this is 3, times 13.25. So if you carry out the calculation, it's 12.405 per unit. So this video about fault on low voltage side, the X side, which is a line to ground. So I calculated the sequence components of the current that will flow through the high voltage and low voltage. Now, what is the current that will flow through phase A? So the current that will flow through phase A is just the positive sequence current through the high voltage plus the negative sequence through the high voltage plus the zero sequence current through the high voltage, which I already calculated. 6.8 plus 87 plus 6.87 plus 12.405, which is 26.145 per unit. So that's in per unit. So that is the current that will flow through phase A of the high voltage winding of the transformer. So what is the base current if I want to convert the per unit to actual amps? So the base current of the high side, so I said 270 MVA divided by 345 kV times square root of 3. So you get 167 amps. So the current that will flow through phase A, so this means phase A of the high voltage, probably I should write H here just so it indicates it's the high voltage. This is the high voltage. Phase A is 26.145 per unit times 167 amps, which is 4.4 kiloamps or Ka. So if a line to ground fault occurs or happens on the low voltage winding or low voltage side, the high voltage winding will see 4,400 amps. So it has to handle that current, basically, what I'm trying to say. So in words, the high voltage winding should be braced for 4.4 kiloamp. This is symmetrical. Obviously, you can calculate asymmetrical. But like I said previously in other videos, this is just line to ground fault happening on low voltage side. But so the high voltage winding has to be designed at least to carry this current, but then you have to calculate the three-phase fault and also the three-phase short circuit fault, then the line-to-line fault and line-to-line to ground fault, and the highest of those should decide what the high voltage winding needs to be designed for. So, and I calculated the zero sequence current through the tertiary is 0.8449 per unit. Let's assume I have a base Sorry, I have to go back. I realize since this is 100, sorry about that. That's 100 MVA base. Because if you remember when I started the video, I said all the impedances are on 100 MVA base. So I want to make sure I correct that. So it's 100 MVA divided by, let's say this is a 7.2 kV winding times square root of 3. So the current would be 8,019 amps. So the actual current the tertiary will see is 0.8449 per unit times 8019 amps. So if you calculated that, it would be 6.8 Ka. Again, this is symmetrical. Just I want to clarify that. So the tertiary has to be designed to handle at a very minimum 6.8 Ka. So that's what the tertiary, the delta winding that I showed earlier. I showed the delta winding with one corner or one corner of the delta is grounded. So each winding, so basically this is a winding. This is a winding. Since it's three-phase, there are three of them. So each of these, because I0 will flow, or the zero sequence basically, only the zero sequence will flow through these, so it has to withstand at least 6.8 Ka. So for this line to ground fault on the low voltage side, the current that phase A of the low voltage we'll see is the positive sequence current of the low voltage plus the negative sequence current plus the zero sequence current. And I already calculated these, so this is just 6.87, 6.87 plus 13.25. So it's 26.99 per unit. So Ix base is 100 MVA divided by 138 kV times square root of 3, which is 418 amps. So the low voltage winding in the phase A current is 26.99 per unit times 418 amps, which is 11.28 kA. Symmetrical. So for this line to ground fault on the low voltage winding side, the low voltage winding needs to be able to handle this current. So that was it for this series. So I hope you enjoyed this video. So basically I started with a system. It kind of applied symmetrical components, network sequences. Then I calculated the equivalent impedances, then all the relevant currents, and determined, like what the high voltage, low voltage, and also the tertiary need to be designed for, the currents basically. Thank you and have a great day.